What do X-rays, microwaves, and rainbows have in common? Well, they're all light. Maybe you guessed that. They're all waves of varying electromagnetic fields. And most of the light around us turns out to be invisible. Like X-rays that image our bones, or microwaves that heat our food, or radio waves that our cell phones use to communicate. We can't see them. Other light is visible, like the light you're seeing right now. But light isn't just a tool, it's a gateway to wonder. It lets us take in the faces of our loved ones and peer into the depths of the galaxy. Light is some cool stuff. For the next 10 minutes, you'll take in a very highly patterned form of light as you watch this physics video. Let's learn. Let's begin by reviewing our lesson objectives. First, we'll introduce the electromagnetic spectrum. Then we'll consider how light interacts with matter. And lastly, we'll examine the applications of the electromagnetic spectrum. Let me remind you that light is just a varying electromagnetic field. So there's an electric field in light and a magnetic field in light. And they get stronger and weaker. That's what that varying part means. They're also perpendicular to each other, which is pretty challenging to picture, but here you see in red the electric field going up and down, and in blue the magnetic field going forwards and backwards. Now, the wavelength, recall, is the distance from one peak strength in field to the next peak strength in field. And we can actually organize all light by this wavelength. So light can be organized by wavelength. When we do that, we call that the electromagnetic spectrum. We're going to go through the electromagnetic spectrum one category at a time. We're organizing all the light by wavelength, and on the far left you see a really long wavelength, 5 billion nanometers, which works out to be about 5 meters. On the right you see a really short wavelength, 0.0005 nanometers. So the distances between those two peaks can vary a ton. At the longest wavelengths we have radio waves. Radio waves are really important because we use them for our beloved cell phones. Cell phones communicate to cell phone towers with radio waves. So cell phones use radio waves to communicate. Radio waves pass through most objects, and that's what makes them good for communication. We can send them through our walls, through our cars, and they'll travel out and still reach the cell phone tower. They can go through trees, and that means that our radio waves are really useful to communicate because they won't be blocked by most things. Next on our electromagnetic spectrum, we have microwaves, and they're really useful as well. You probably know that you use microwaves to heat your food, and that's literally using light to heat your food in the microwave range. But we can also use microwaves for things like radar. So this giant dome here can detect the position of that plane by shooting out microwaves and then seeing when they bounce back, because it turns out that microwaves reflect off of airplanes. So radar uses microwaves. And the radar lets us know the position of planes all over the place. The reason microwaves are used for radar is because microwaves pass through most objects, but they bounce off airplanes. Next on our electromagnetic spectrum, we have infrared light. Infrared light is shorter in wavelength than microwaves or radio waves, and it's used to communicate as well. For example, our remote controls use infrared light. That's what's shown there in that diagram. But infrared is also really highly associated with heat, so heat lamps actually use infrared light. This lizard is absorbing a bunch of heat from that red light above. Now the red light is obviously visible, but what you don't see is a bunch of infrared light that's longer in wavelength than the visible light that does a really good job of warming things. So infrared light is used in heat lamps. Here's the thing, infrared light is absorbed by almost everything. And so that means that it would be really bad for long distance communication. You might notice if you try to communicate with your remote control to your TV, that if you block it with your couch even, it will not reach the TV. Infrared light is experienced as heat. So if there's a bunch of infrared light, you'll feel heat, just like this lizard here. Okay, after infrared, what comes next, do you think? Well, it turns out red. So after infrared comes red. That's a really useful mnemonic to keep track of what comes after infrared, and we'll see it has another use in just a minute. Okay, so after our infrared comes visible light, which includes red. only a small fraction of light is visible. So we tend to think of light as mostly that thing we can see, but really the rainbow shows all the colors we can see, from red to violet. There's tons of light outside of that. Everything else on our electromagnetic spectrum is invisible to us, except for Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. Obviously, visible light is used for sight. Why is that? Well, matter around us absorbs some colors and reflects others, and that makes it really useful for distinguishing everything around us. For example, the white light of the sun contains the whole rainbow, as we know, and when that light strikes something like, say, a red apple, the red apple absorbs most of the light except for red, whereas the green leaves absorb most of the light except for green. And so that light is reflected off of those surfaces to our eyes, and that's what we see. This is a little simplistic. It doesn't actually absorb every little bit of every other color of light, but this is approximately what happens. Most of the red light is left behind, and that's the dominant color you see. So remember, when we see the rainbow, we're seeing all the different colors that are visible to us. If we put IR on this Roy G. Biv scale, we have infrared, then red, orange, yellow, green, blue, indigo, and violet. What comes after violet? Any guesses? Here's where our mnemonic comes back again to help us know what comes after the visible range. It's UV, or ultraviolet. So remember that after violet comes ultraviolet. And so we represent ultraviolet light here as coming after visible. Visible light ends in violet, and then comes ultraviolet. Ultraviolet here is represented by sunlight. Sunlight contains UV rays as well as a ton of other different types of light, including visible and infrared. Ultraviolet light is shorter in wavelength than visible. At this point, though, it's important to introduce another way we can categorize all of this light, and that's by energy. It turns out that the different types of light contain different amounts of energy. So radio waves are the least energetic, and the most energetic are going to be on the far right of the spectrum. We'll get there in a second. But UV rays are relatively high in energy, and that is a concern to us. They're so energetic that this happens if you hang out in them. This guy's got a pretty solid sunburn. Why? Because he's been exposed to ultraviolet radiation. So sunlight contains UV light, and UV light may be dangerous. Not all forms of UV light are dangerous, but most are. And so now what we'll do is we'll move to considering just the energy of all of the different portions of our electromagnetic spectrum. And it's important to remember that UV light is high energy. What that means is if it strikes our skin, it can be absorbed by our DNA, and it can actually damage the DNA in our skin. So UV light can damage DNA. That can be bad. It can actually lead to cancer and sunburns, but also we can use it to our advantage. Here we have a bunch of UV light exposed to a bunch of masks. Those masks are being sanitized. So they might have microbes on them, and they're being killed by the UV light. The UV light is absorbed by the microbes, damages the microbes' DNA, and those microbes die. So while UV light can be dangerous, we can actually use that to our advantage. UV light can be used to kill microbes. Okay, after ultraviolet comes X-rays. X-rays are even higher in energy than ultraviolet light. Of course, we're most familiar with X-rays because they can image our body. And that's because they pass through our soft tissue pretty well, but don't pass through our bones as well. And so we can take nice pictures of those bones. As you know, X-rays can be used to image our bodies. They're also dangerous though. And that's why when you go in to get an X-ray, you're often outfitted with this sweet lead blanket. The lead blanket absorbs all the X-rays so that your body doesn't. And you only keep something, say, your leg, exposed to the X-rays. Why? Because X-rays are high energy and dangerous. So X-rays can also cause cancer, just like our UV light. Okay, last up, gamma rays. Gamma rays are the highest energy form of light and the shortest wavelength. Gamma rays are also dangerous. Once again, though, we can turn that dangerous light into something that helps us. This is a device used for radiation therapy. So if you have developed cancer, which is unfortunate, you can kill that cancer with gamma rays. So this giant device's only purpose is to aim gamma rays at the tumor or whatever cancerous cells you have and to kill those cells. So gamma rays can be used to treat cancer. All right, now let's practice putting all of that information to use. There's two parts here that I want you to do. Part A says place the following categories of light in order of increasing energy. So from lowest energy to highest energy. And then next, list an application for each category of light. There's actually a table here, a blank table on your notes that you can fill in with these answers. So pause the video and give that a try, and then I'll show you what you should have seen. All right, well, you should have ordered the light in this way: radio, microwaves, infrared, visible, ultraviolet, X-rays, and then the highest energy of all, gamma. Next to these categories of light, I've listed an application for each one. We did discuss multiple applications for some of these light categories, so in that case, you could have multiple answers. Let's review what we've learned. First, we introduced the electromagnetic spectrum. It's a way to categorize all the different types of light. We saw that we can organize them by wavelength or by energy. Then we considered how light interacts with matter. And we saw that it depends on the type of light you have. Lastly, we examined the applications of the electromagnetic spectrum. Basically, all of these different types of light form a toolkit to interact with the world around us.
Hey, hey.